Hello students, welcome to our new series, Basic Aerodynamic Theory in Aviator Cloud. Today we will discuss about the principle of continuity. It is very important to understand deeply the aerodynamics for your CPL technical general exam. Okay. Also, in any airline exam, questions will come from basic aerodynamic theory. Okay, so it is very important to understand in detail. So today's chapter overview, we will discuss about the principle of continuity, Bernoulli's theorem, and streamline or stream tubes. Okay, mostly it will why and how. First, the fundamental laws of the universe. Aerodynamic theory is built upon the basic physics law. The most critical one in this chapter is energy and mass can neither be created nor destroyed, only changes from one form to another. Okay, this is the leads to our principle of continuity. This is conservation of mass, right? Conservation of mass and energy. Even in any airline interview, even this question can be asked. Okay, so energy and mass can neither be created or destroyed, only changed from one form to another. You already studied this in your most probably 8th standard. Okay, so today you will apply these things in your aviation studies. So this is the fundamental laws of universe. Now we will have to understand what is the principle of continuity. So to demonstrate the principle, we consider a streamline flow. So what is streamline flow? I'll explain you later. Streamline flow is a flow where all the molecules follow a straight path, okay, one by another, and one path will not cross the another path, right? And the velocity will be constant. They will go like this. You can consider this like the railway tracks. Okay, so two railway tracks, you will see it is always parallel to each other every place, and they don't mix with each other. Okay, so that is you can say as a streamline flow of air or tube that has a reduced cross-sectional area in the middle. So we will consider a streamline flow in a tube. Okay, we will take a tube like this, and we will see what happens in the tube when air flows through the tube. The amount of air entering to the tube must equal the amount of air leaving it. This is the basic of your all principle. So what it says, that the amount of air entering to the tube, let's say this tube, the amount of air is entering 10 kg. Okay, the same amount of air has to leave through it, so 10 kg has to get out also. Okay, so this is the principle. Now what happens in between, we will discuss. So now here you see we have a tube with varying diameter. That means the diameter here at the entrance is more and diameter output is less. Even the cross-sectional area in between even is lesser. Okay, so what happens, the mass flow, as I told you, 10 kg. So this 10 kg is actually a product of the cross-sectional area. Let's say this side A1 is the area, that means the cross-sectional area, multiplied by the velocity of the air, let's say V1, multiplied by the density ρ1, okay, is equal to 10 kg. So mass flow is a product of area, velocity and density of the air, 10 kgs, and this 10 kg has to be here also. So it is also equals to A2 multiplied by V2 multiplied by rho 2 density. Okay, so what happens? So A1 V1 rho 1 is equals to A2 V2 rho 2. Okay, if we don't consider rho 1 and rho 2, let's say same, I mean the velocity, the density is not changing, then A1 V1 is equal to A2 V2. That means if the cross section reduces in the A2 area, the velocity, you see, V2 has to increase to remain constant. This is the principle. Very simple. So what we understood, the mass flow must remain a constant value at all points along the tube. That means A into V into rho is constant. A cross section area, rho is the density, V is the velocity. Okay. Now air as a fluid, is air compressible? Yes, air is a compressible fluid. Any pressure change in the flow will affect the air density. If the pressure is high, the density will also be high. If the pressure is less, the density will also be less. Already in your flying, you know, when you are flying at higher altitude, the density of the air is less because the pressure, static pressure, is less at high altitude. You already know. At lower altitude, the pressure is high, the static pressure is high, so the density is also high. However, for basic aerodynamic theory at lower speeds, we can make a simplifying assumption, because when we are discussing the aerodynamic theory, we will consider this density changes as insignificant. So what happens? What is our assumption here? At low subsonic speed, which is below 0.4 Mach, density changes are insignificant. For practical purposes in this range, we can disregard changes in density. So we take density as same or constant for lower speeds. Okay, this will help us to understand our theory better. So that's why we call A into V is equal to constant. So velocity is constant divided by area. Now area versus velocity, this relationship we need to understand, because the mass flow must remain constant. As I told you that 10 kg, if area decreases, velocity must increase, right? So if this is your tube, so what we understood, let's say this, what we understood, if area decreases, here the area decreases, the velocity has to increase. Okay, if area increases, velocity has to decrease. Here the area is increased, velocity has to decrease. So this is the thing. So MCQ question comes from here. Okay, in a cross-section area, if the area decreases, what will happen to the velocity? It will increase, decrease, remains same. Okay, remains same, or cannot determine. So your answer will be increase. Now predicting velocity. The equation of continuity allows us to predict velocity changes mathematically. Okay, we can predict this mathematically. I will just show you quickly. We don't need to do this for our CPL studies, just for your understanding. It is crucial to understand how air behaves when passing over an object, a specific shape like wing, valid for speed less than 0.4 Mach. So Bernoulli's theorem. Now we will study about the Bernoulli's principle. It is the relationship between velocity and pressure. Okay, the relationship is defined as Bernoulli's theorem. This question comes in interview, any interview, your even cadet pilot interview. Okay, cadet pilot interview, even your airline interview sometimes. Okay, airline interview sometimes, or your SPL interview, CPL, SPL interview, it may come. The theorem. Okay, in the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant. I say again, in the steady flow of an ideal fluid, let's say air, okay, in the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant. What does it mean? Okay, before that, ideal fluid, what is ideal fluid? It is incompressible and has no viscosity. Generally, normal fluid or air, it is compressible. We know air is compressible, physically compressible, and it has some viscosity, right? But for our understanding, we take air as incompressible. Also, we saw below 0.4 mark the rho density is very insignificant, so that's why we are sensing it as incompressible, okay, and has no viscosity, so we call it as an ideal fluid. So question may come, what is an ideal fluid? Even MCQ can come, okay. So it is incompressible and no viscosity. So what does the theorem says? In the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant. So that means, like, okay, that means the P is the pressure or the static pressure, okay. P is the static pressure and rho v square is the dynamic pressure. Already you know how this half rho v square comes, already you know, okay. We don't need the derivation, we just need to know that half rho v square is the dynamic pressure. Now half rho v square, here rho is the density, v is the velocity, right? Velocity. So already you know, if velocity, cross sectional area reduces, velocity increases. Now this formula of the Bernoulli, the static pressure and the dynamic pressure is constant. This is the basic. So what, memorize things, static pressure and dynamic pressure is constant. What does it mean? It means, look at this Venturi tube. The tube throat here is bigger, okay. Now when you go here, it is converging and the area is reduced. Again it is diverging and the area is as previous, okay, previous. So what happens, as we know, a1 rho 1 v1 will be equal to a2 rho 2 v2. Also, when you come here, when the cross section area is reduced, your velocity has to increase, okay. Like this, it is going slowly. Now here it has to go faster, so velocity has to increase. When your velocity increase, that means v will increase, that means half rho v square will increase, that means the dynamic pressure will increase. So when your dynamic pressure increases, Bernoulli says P plus half rho v square is constant. That means this dynamic pressure, half rho v square, is increasing. To make the equation constant, the P has to reduce. That means here the static pressure has to reduce, right? Reduce. Now how will you understand that static pressure has been reduced? Now look at this tube here. This is for your understanding. Look at this tube here. Now this tube, if the static pressure, let's say here the static pressure value is 5, just 5, okay. Now the height of this tube, this liquid here, goes up to the top, okay, up to top. This is 5, this liquid goes to top, so this is 5. Now here the static pressure has been reduced. That's why this tube, the fluid at this tube has come down. Let's say this is 3, okay, 3, whatever you can call it, 5 centimeter this tube length, and this is 3 centimeter. That means clearly we can see the static pressure has been reduced. If we can do this experiment in our lab, we will be able to see this. Okay, this is what we understand. So just do not try to understand and try to figure out how it happens. Okay, this is very important for concept building. So next, they are giving some practical example. I have taken some practical example. I am not going for this mathematical terms, but see here static pressure 101325 Newton meter square, static pressure 1225, and your velocity is 100 knots. That means let's say 52 meter per second. What happens? Dynamic pressure will be half rho v square, so half rho v square is 1656 Newton. Velocity was 52, okay, 5 meter square. So according to the Bernoulli's principle, this is the static pressure, this is the dynamic pressure. Total is 102981 Newton per meter square. This has to be constant, right? This has to be constant. Now if the dynamic pressure increases, what will happen? Let's earlier now to static pressure value, you can see previous static pressure value was 101. Say next, now let's say this tube is being narrowed, right? This tube is being narrowed here, A2. This tube is being narrowed. So what will happen? Double the velocity. Let's say the velocity will has to be double. We are doubling the velocity as 104. 52 multiplied by 2, 102. Now put it in the formula. It comes 6625 Newton per meter square. Okay, the new dynamic pressure. Previous to 5. So static pressure will be total pressure minus the new dynamic pressure. The new static pressure is 96356. What we need to see, what we need to understand, this new static pressure value is less than 101325 was the previous P. New P is 96365. This is just mathematical representation. You don't need to remember this, or you need to do this calculation. What happens? This is for your understanding. Now total pressure terminology, what does it say? The constant static and dynamic is referred to several names in aviation. Yes, we know it as total pressure, pitot pressure, stagnation pressure. Stagnation pressure, okay, you remove it, so we call it total pressure or pitot pressure. Okay, the static and dynamic is total pressure. Total pressure is equal to static plus dynamic, P plus half rho v square. Lot of MCQ questions comes from here, lot of, okay, every year, even in your CPL, in any other exam also. So even it is applicable for cadet pilot exam also. So what happens? MCQ will come like this: total pressure is equal to option A, static plus dynamic, static minus dynamic, something like this, something like this. So you know static plus dynamic. Even they can reverse the question. Dynamic pressure is equal to, okay, total pressure P, total P minus static. This kind of questions also come. So you have to, if you go to the question bank, I will provide you question bank, you will find this kind of questions. Okay? Next is the practical application. How does an aeroplane fly on this Venturi tube? The Venturi tube is just a demonstration. To fly, we use a specially shaped body, the aerofoil. The principle remains the same. So what we discussed in this Venturi tube, right? The same principle, the same thing actually happens. I mean, the same happens in your aerofoil. Now you can see this is the shape of an aerofoil. Now what is an aerofoil? I hope many of you already know. If you don't know, let me explain. So this is an aeroplane. Let's say I am very bad in drawing, but this is an aeroplane, okay? Right? This is an aeroplane. Fine. So this is the wing. Now let's say we cut the wing. We need the cross section of the wing, so we cut the wing here. Okay, so when we cut the wing here, we get a shape, a side shape of the wing, something like this. Something like this, right? There is a middle line, we called it. It is camber. The straight line would be the chord. Let's say this is the chord line. Chord line. We will explain, we will learn about it later. Chord line. So what I want you to observe is that this line, this aerofoil, you see the curvature here is more and the curvature below is less. This is streamline flow, okay? Streamline flow. So this is the curvature is more like this. So if we take a boundary, an imaginary boundary, let's say this is a tube, imaginary tube. Imagine this is a tube. So if this is a tube, okay, the tube we discussed earlier, let's say this is a tube, imaginary tube. Now in this imaginary tube, you see the cross section area here is more and the cross section area here is less because of the curvature of the wing. So now you can apply your whatever theory you already studied, you can apply your theory, and this theory will lead us how does this aerofoil produce lift. We will discuss it later. Just to explain you what is an aerofoil. Now you see here this ear is like this, bending like this, bending like this. So the cross section here, sorry, the cross section here is more and the cross section here is less. Okay, so do not just follow this tube. The only the tube is not only the example, the aerofoil is also an example. Okay, now already I discussed about what is a streamline. Streamline is the path traced by a particle of air in a steady airflow. Okay, so streamline cannot cross, close together, increase velocity, far apart, decrease velocity. So I told you streamline flow is like this. Let's say railway track. Railway track never converge or diverge. They are parallel to each other. But streamline flow can converge or diverge, but they will not cross each other. If they cross each other, they will become turbulent. Understood? Now what is converging airflow? And let's say this is an airflow. You see, this is streamline only, but they are converging. So when it converges, you see here the molecule here, let me draw it, the molecule here and the molecule here. So this molecule here speed is low, this molecule will accelerate here, right? And as the molecule accelerates, because of the Bernoulli's principle, the dynamic pressure is increasing, half rho v square is increasing, so static pressure here is less, right? The opposite things happen here in diverging. Let's say this is the airflow like this, diverging, right? The opposite thing will happen. So flow will decrease here. That means the velocity will decrease here. Velocity decrease and static pressure increase. So not only pressure, the static pressure will increase because of Bernoulli's principle. Okay. This one, remember? Okay. Diverging airflow. So this is the stream tube. Now we call it, if we take a tube, this kind of shape will come. A stream tube is an imaginary tube made of streamlines. Key property, there is no flow into or out of the stream tube through the walls. Flow is only along the tube. Okay, whatever. But for our understanding, let's say if there is a tube, this is a diverging tube. Okay, this. So what is the summary of continuity? Speed below 0.4 Mach. The air accelerates when the cross-sectional area of a streamline flow reduced. Air decelerates when the cross-sectional area increases. Already we learned this. Next, then summary of Bernoulli, already we learned. If a streamline flow accelerates, kinetic energy increases, static pressure decreases. If a streamline flow decelerates, kinetic pressure decreases, static pressure P increases. Lot of MCQ questions comes here. Okay, I will give you the MCQ questions end of this video or in the description box. By harnessing these principles with the aerofoil, aerodynamic force lift is generated. Here. Now comes for the assessment. If the cross-sectional area of an airflow is mechanically reduced, what is the correct option? The velocity remains constant and kinetic energy increases? No. The velocity remains constant and mass flow increases? No. The mass flow remains constant. Yeah, this much is correct. And static pressure increases? No. The mass flow remains constant, yes, and velocity increases. This is correct here. Okay. The statement pressure plus kinetic energy, this is static pressure. Okay. Static pressure plus kinetic energy is constant, refers to Bernoulli's theorem. Here. If the velocity of an air mass is increased, velocity increase, that means V increase, that means half rho V square increase, that means dynamic increase. The dynamic pressure will decrease? No. The static pressure remains constant? No. Kinetic energy increases? Yes. That means dynamic, half rho V square increases. Dynamic pressure increases? Yes. And static pressure decreases? Yes. Because P plus half rho V square constant. So half rho V square increasing. So P has to what? Reduce. Right? This is the correct answer. So this kind of questions will come. Okay, this is for your understanding. The mass flow stays constant. Okay, we don't need to see this. Now, diverging streamline indicates. What does diverge means? Decelerating airflow. Yes, with resultant increasing static pressure. Right, diverging. Understand? Like this. So what happens? When it is diverged, so velocity will decrease and static pressure will increase. If the pressure on one side of a surface is lower than the other, the force per unit area exists. A force per unit area exists acting towards the lower pressure. Now this is actually how lift is generated. This question is asking. Whatever, let me explain. So this is your aerofoil, right? This is your aerofoil. So what happens? What is it saying? If the pressure on one side of a surface is lower, static pressure, okay? So upper surface static pressure is low. Then the other. So lower surface static pressure is high. Now what does your basic sense understand? Pressure from high pressure area to low pressure area, there will be a force. Now this force will produce lift. Okay, so a force per unit exists acting towards the lower pressure area. Yes, from the high pressure area to the low pressure area, it will act. Next, regarding a stream tube, which statement is correct? It is an imaginary tube where there is no flow through the walls. This is a property, this is a condition, okay? You have to remember this. There is no flow through the walls. We already discussed. At flow speeds less than 0.4 Mach, which is insignificant. the changes in density due to dynamic pressure. So rho we take it insignificant. That means due to dynamic pressure. That means let me explain this. Let's say dynamic pressure half rho v square. But you are flying very low speed, 0.4 Mach, less than 0.4 Mach. In that case, what happens? This aerofoil in higher speed, what happens, air comes here, it gets compressed, okay, because of very high speed it get compressed. But your speed is low, this compression is so insignificant, okay, so that's why the density due to dynamic pressure is insignificant. In accordance with the principle of continuity, changes in cross-sectional area will affect air velocity. Yes, already we have seen this. Changes in cross-sectional area here with air velocity. Yes, air velocity less, air velocity is more. According to Bernoulli's theorem, if a streamline flow accelerates, kinetic energy increases. Acceleration means velocity is also increasing, so half rho v square increasing, so dynamic increasing, that means kinetic increasing, so static has to reduce. Energy and mass can neither be created or destroyed, only changed from one form to another. This refers to the principle of continuity. You need to remember this. Thank you. So this is our first lecture today. In the next lecture we will discuss about lift, generation of lift, then drag. So basically we will cover the whole aerodynamics one by one. And also if you want to join our class, then you can go to aviatorcloud.com